Hi, Caitlin. Congratulations on winning an award as one of the rising stars of separation science. How did it feel to be recognized with the Outstanding Achievement in Gas Chromatography Award?
Oh man, it was really an honor. So that kind of pretty much summed up my entire 5 years of my PhD being recognized with that. I switched fields recently from going from gas chromatography into liquid chromatography. And so to see the achievement of like having my entire PhD being recognized with that award, it was really special because that was work that I was really excited about and really cared about. And I'm glad that other people saw the value in it as well.
Absolutely. Well, on behalf of Organimation, we were very proud to sponsor the award. And out of curiosity, had you heard of Organimation or used nitrogen evaporators previously?
No, so this is the first time that I was hearing about this company. And in terms of the sample prep that we would do in our lab for GC analysis, we never really worked much with evaporation or those types of extraction methods. So it's really interesting to actually learn a lot more about your company and about that form of sample preparation through winning this award.
Very good. Just to give you a little bit of background, where we come into play is post extraction when organic solvent needs to be removed, working with samples from 50 mil and under, what I would consider test tube level, and concentrating them down to maybe a GC vial at 2 mil or even down to dryness for like some of the PFAS drinking
Mhm.
water methods. Not to throw you a curveball right off the bat, but one thing I am hearing and want to dig into further is it seems like LC is becoming a lot more popular compared to GC. A lot of applications seem to be making that switch. Do you have any insight on that?
Yeah, as someone that has flip-flopped back and forth in my research, I did LC in my undergrad, then I went to GC for my PhD, and now I'm back to LC for my postdoc. I don't think it's necessarily a situation of like one technique becoming more popular than the other. I think it's really more so they're both excellent techniques, just aimed at different applications. So I think like somewhere where GC analysis is really great at is in a lot of like your petroleomics type fuel analysis and a lot of your food analysis as well, where now LC is really a lot better at doing a lot more of the metabolomics type separations and maybe some even like the proteomics that we're seeing. So I think they're both like really excellent techniques. They're just aimed at solving different application problems. But something I'm really interested in as part of like my career path and looking towards the future is trying to like bring both the GC and the LC back together to answer problems, like look at stuff from both the volatile and the non-volatile side.
I really appreciate you expanding on that. Yeah, that makes a lot of sense to me. Just generally speaking, what drew you to the field of analytical chemistry and particularly chromatography?
Yeah, I've always been a chemistry type person. My mom is a high school chemistry teacher. Apple doesn't fall far from the tree there. And so when I was in my undergrad, I was pursuing a chemistry major and trying to look at expanding my major, getting involved in some undergraduate research. And I had two really excellent mentors, Dr. Sarah Rutin and Dr. Marianne Collinson, who let me into their lab. And that lab was focused on developing stationary phase gradients, so new types of column modifications for LC columns. And as an undergraduate, they basically treated me like a graduate student. I had my own project, I could set my own deadlines and goals. And through doing that project, that's really where my love of chromatography came from. I don't know, something about seeing peaks coming off a column and seeing that either your modification worked or it didn't work, and the anticipation of that just really drew me into chromatography. And so that kind of then led me down the path of pursuing my PhD and now doing postdoctoral research.
That's great to hear. What advice would you give to early career scientists aspiring to make significant contributions in analytical chemistry?
Yeah, it's interesting giving advice because I still think I'm very early career, so I don't know how much insight I can give. I really try to focus on in my research is always expanding out and thinking about the broader picture, right? So it's one thing to focus on a specific application or focus on a specific technique such as GC or LC, but I always like to try to think about like what's the broader thing in chromatography or what can I learn doing LC research that I can then go back and apply to GC research. So trying to always make connections and intertwining things. I think that's where a lot of really great science occurs is at those types of intersections. And then with that, I mean, you're going to have a lot of failures. I have a lot of really bad ideas half the time. And so you have to just embrace that failure as well and just take it as another learning opportunity to help you just keep going down the curvy path of research and all.
How do you see innovations in analyte discovery impacting the field of separation science in the coming years?
Yeah, I think this is something that drives all of us, like chromatographers, is we always want to try to improve resolution, improve the number of peaks that we can get, the number of analytes that we can separate. So I think with that, we can get both instrumental advances and also computational advances. So on the instrumental side, I always think back to trying to improve some type of column technology. So in LC research, that might be continuing to fabricate new types of LC columns with different chemistries, trying to go smaller from C column analytical scale to a capillary scale column that would also increase your peak capacity. Same thing in the GC side, we can think about continuing to modify those chemistries and then also doing multidimensional separations, which is what a lot of my PhD research focused on. And then computationally, one really interesting fact is continuing to go down this path of non-targeted analysis where we try to maximize resolution the best that you can in a separation, but then leave a lot of it up to some mathematics to help us try to extract out those analytes, especially the meaningful ones that might have some type of statistical significance. So with a lot of that computational work, I think it's really interesting, some of the stuff that we're seeing with machine learning and artificial intelligence coming up. And that's stuff that I'm starting to play with in my research. And I think that will continue to drive the field forward.
Absolutely. I really enjoyed getting to review the research that you sent over, and I was hoping that we could talk about the recent work that you published last year, I believe. You focused on investigating potato taste defect in coffee, and I was curious how that project came to be.
Yeah, that project was really interesting. It was through a lot of collaborations. So first, this coffee roaster that goes and tries to ethically source beans in different regions of Africa. They first approached some researchers at Seattle University, which is a primarily undergraduate institution, to just try to investigate these coffee beans, try to figure out if there are any differences or not, and also quantifying a known biomarker of potato taste defect, which is 2-isopropyl 3-methoxypyrazine. So these researchers at Seattle University, they were the ones that got all the beans from this coffee roasting company and kind of started doing some of the initial quantification. What they found was that obviously coffee is a very complex matrix. There's hundreds of peaks in there, and they thought that some other stuff might be changing. So that was when they then approached my PhD lab at the University of Washington saying, hey, you guys are experts in this technique called comprehensive two-dimensional gas chromatography that's supposed to really increase resolution for all of these different types of volatiles that we're seeing. And you guys also know how to do a lot of the non-targeted analysis to help us improve discovery of things that we might not even know that's changing. Would you be interested in joining along? So that was how I got involved in that project.
That's awesome. Yeah, and I was hoping we could get into that a little bit. Certainly, I've seen it in writing, but I haven't reviewed too much research that included comprehensive two-dimensional gas chromatography. So I was hoping you could talk about some of the advantages that has over the traditional one-dimensional GC for complex samples.
Yeah. So as we know, with one-dimensional GC, we input in a sample onto our GC column. It gets separated by that column based primarily upon boiling point, and then it will reach our detector. So say like a mass spectrometer, an FID detector, something of that sort. With GC-GC, what we're doing is we're taking that sample, having it go through that first primary separation, and then instead of reaching the detector, we have a second column that is connected. And so these two columns are connected using a modulator. So that's going to take out very tiny chunks of that first dimension effluent and re-inject it onto that second dimension column that has some sort of complementary selectivity. So through that continuous separation of using a 1D column and a 2D column, we are ultimately providing not only increased selectivity for a lot of these analytes by using different columns with different chemistries, but we're also improving our peak capacity. So by improving our peak capacity, which is how many peaks can we shove into a chromatographic space, we're ultimately improving the resolution that we can have. So if you imagine sometimes in a 1D chromatogram, you see this unresolved hump of peaks. In a 2D chromatograph, we can actually improve upon that unresolved hump and help actually resolve out a lot of those analytes.
Wow, that's very interesting. How did you optimize the headspace solid phase microextraction conditions for extracting coffee volatiles? And you could talk about some of the challenges in that process.
Yeah, I do think that's always like the fun thing, right? Is we had a solid sample, we had to somehow put it into the gas phase. So, our collaborators at Seattle University, since they were first just trying to quantify that known biomarker of potato taste defect, IPMP, 2-isopropyl 3-methoxypyrazine, they had already started with an initial SPME method that we could work off of. The problem was that their SPME method had a 60-minute extraction time at a very low temperature. And for someone like me who wanted to try to run hundreds of these samples in one giant batch on our GCGC, having that long of an extraction time would only increase the total amount of runtime on the instrument. And so I wanted to really try to balance not only maximizing the analyte signal that we got using the solid phase microextraction, but also try to maximize our run throughput and total amount of analysis time. So for me, that meant optimizing both the SPME extraction temperature and also the time. So what I found in doing some of those preliminary studies was that we could increase the temperature and decrease the extraction time by half, and we still were able to recover the same amount of analyte signal as we did using the original method.
That's great. Your research identified 359 class distinguishing analytes related to PTD. What were some of the most surprising or significant findings from this comprehensive volatile profile?
Yeah, I think there were a lot of really interesting things that we found in that analysis. So, first thing was what was really well established in the literature was we knew one analyte changed between potato taste defect and non-affected coffee, that IPMP compound. So, one, it was really interesting to find, well, actually, there's 358 other things that are also changing in the headspace. The second thing that was really interesting was that a lot of the analytes that we found, around 300 of them, had the strongest or highest signals in the clean coffee samples and then lost signal when affected by potato taste defect. So there was this major dropout of signal in the potato taste defect coffee samples. And a majority of those 300 analytes that lost signal in our potato taste defect samples were volatiles that you really want in your coffee. So a lot of them were things such as pyrazines and furans, and those volatiles are really important contributors to coffee aroma. They're the ones that provide those flavors and aromas of like cocoa, nutty, roasted notes. So having those all just deplete out of our potato taste defect samples means that you're really losing a lot of those good flavors. And then that's only amplifying what you're tasting from the potato taste defect, that earthy, moldy, rotten aroma. Something else that we found that was really interesting in this analysis was of the small amount of analytes that were higher in our potato taste defect samples, a lot of those were things that were phenols and phenylindens. And these analytes are formed during the roasting process due to the degradation of a lot of chlorogenic acids in the green coffee bean. And some other studies in the coffee world have found that microbes tend to increase the levels of chlorogenic acids in green coffee beans. So therefore, when you go through that roasting process, you can imagine that's why we're seeing a lot of these phenol and phenylindens is due to that initial microbe infestation that might be occurring as a result of potato taste defect. So I think there were 3 levels to some of our interesting results, but hopefully you're getting us a little bit closer to that picture of what potato taste defect actually means.
When I was drafting these questions, I decided I couldn't ask you why was potato taste defect bad or what was the problem. I figured it was a little too self-explanatory that potato taste defect was impacting coffee.
Yeah. No one wants their coffee to taste like potatoes.
No, absolutely. Or, well, and also losing all of the great attributes, like you mentioned.
Yeah.
Finally, how do you think your research could help coffee farmers or the coffee industry in general dealing with this defect?
Yeah, something that's a little bit frustrating when we were doing a lot of this research is that potato taste defect is a very understudied flavor defect in coffee beans. There's just not a lot of research out there as to what causes it, why does it happen, etc. So I think by us having created this whole volatile profile of potato taste defect, we showed like, okay, this is what's happening to the coffee beans. So now farmers and roasting companies can take that and try to start developing solutions on how to prevent it. So hopefully they will be able to maybe dedicate more resources and trying to battling new ways against the intestia bug that feeds upon these plants that kind of leads to potato taste defect. And then also dedicate more biochemical resources to how do we get from this bug feeding on the coffee plants to all these different volatiles that we observed in our GC-GC analysis. What are the biochemical pathways that contribute to that? Because again, that could be developing new, ultimately lead to developing new ways of how we can combat it in the end and ultimately ensure that a lot of these farmers over in Africa are able to sell their crops at very high prices and be able to make a nice living for themselves.
Is there anything we missed? Is there anything else you'd like the audience to know about this work?
No, that pretty much, yeah, that kind of covers it all.
The two dimensional GC was something that was really interesting to read about. But congratulations again on the award, and I really enjoyed our talk.
Yeah, thank you so much. And thank you, Organimation, as well, for sponsoring my award.